the same confined space, there is an infinite number of parallel realities that actually can create a powerful or less powerful form of God equals MC squared as we know it.
What if a single conversation had the power to shift everything we thought we understood about the universe? Deep beneath the ground in Switzerland, an enormous ring of powerful magnets drives beams of particles to speeds approaching the speed of light. Some people claim those violent collisions have ripped open a gateway to another world. Today, we dive into that rumor through the perspective of Joe Rogan and a 13-year-old boy. We ask the questions that spark wonder, chase the facts that bring us back to Earth, and trace the journey from wild rumor to scientific reality. But this was not just a heartwarming interview with a bright kid. As the conversation moved forward, something unexpected unfolded, something that gave even Rogan a moment of pause. Was Max picking up on patterns that nobody else had noticed? When Joe Rogan first came across Max Laughlin's physics videos, he did not hesitate to reach out. Max is 13 years old and posts content under the handle at Max Laughlin on TikTok. His short clips tackle topics like memory quirks and particle collisions. One particular video about the Mandela effect using colored cards crossed 5 million views. That clip traveled fast across the internet, eventually landing him an invitation. In February 2025, the production team called him in for episode 1912 of the Joe Rogan Experience. Max spent 2 full weeks going through official CERN reports and watching short documentaries on the Large Hadron Collider. On April 10th, he flew to Los Angeles and walked onto the set, where he was greeted by Rogan and his crew. They settled into a simple studio with 2 chairs and a round table. As the cameras began rolling, Rogan introduced Max as someone with a rare talent for breaking down complicated ideas. He then asked Max how his obsession with science first began. Max explained that he built a telescope at age 8 just to get a closer look at moon craters. After that, he put together a working radio using soldering tools to understand the basics of electronics. He also took first place at his county science fair for a homemade cloud chamber that made particle paths visible to the naked eye. Rogan brought up the viral claim about CERN opening a portal. Max described the facility as a 27-kilometer circular tunnel beneath Geneva built for smashing protons together. He laid out the core mission, to recreate conditions from the earliest moments of the universe and hunt for new particles. He also pointed out that CERN makes every single result available to the public, and not one report mentions anything resembling a portal. Rogan remarked on how quickly wild stories travel across social media. He asked Max how he goes about verifying unusual claims. Max said he always starts with the official lab websites, then moves on to trusted physics blogs and recorded lectures from university researchers. At one point during the conversation, Max grabbed a piece of paper and sketched out a rough diagram of the collider. Their exchange stayed grounded in real facts throughout. Rogan mentioned that Max had reviewed dozens of summaries from high-energy physics organizations before even stepping foot on the set. Max Laughlin is genuinely exceptional. It is almost unbelievable that a 13-year-old could hold this level of understanding on such deeply complex subjects. That kind of mind appears maybe once in a million. His insights have since sparked serious conversations among figures in the scientific community who are trying to make sense of what Max has revealed. But here is the twist. Max was not simply reciting memorized facts. He spoke with the quiet confidence of someone who had seen something clearly, something he could not push from his mind. So what exactly had he uncovered? Beneath the fields along the border of France and Switzerland sits a tunnel that stretches 27 kilometers in a loop. Inside that ring, machinery operates around the clock. Liquid helium keeps the environment chilled to minus 271 degrees Celsius, colder than open space between the stars. Superconducting magnets line the walls and keep particles locked onto a precise circular path. 2 separate beams of protons travel around the ring in opposite directions at the same time. Powerful radio waves give them a push on every lap, building their speed. Sensors check their exact position thousands of times every second. Once the beams hit full speed, they are directed into collision points. At those spots, protons meet head-on and release energy that mirrors the conditions of the universe just fractions of a second after the Big Bang. Every collision produces a burst of new particles flying outward in all directions. Massive detectors surround each collision point, built from layers of metal and silicon and resembling enormous cameras. Atlas and CMS are the two largest among them, each weighing thousands of tons. They capture the full spray of subatomic debris from every impact. Tiny chips log data on mass, charge, and velocity. High-speed electronics convert those readings into digital information instantly. All systems are tested thoroughly before each operational run. Technicians monitor every channel to catch issues before they become problems. Above ground, engineers sit at control rooms packed with screens and control panels. They oversee beam injections, magnet currents, and all safety systems simultaneously. Thousands of computers collect and process the incoming data from every experiment running at once. That information is distributed across a worldwide network of data centers. Scientists from more than 100 countries connect remotely to dig through the results. Research teams gather daily to go over findings and plan upcoming runs. The work at CERN orbits around a few central goals. One is understanding the Higgs boson, the particle responsible for giving mass to others. Another is searching for evidence of dark matter, the invisible substance that holds galaxies together. Teams also investigate how gravity operates at microscopic distances and whether space itself follows known rules when particles are pushed to extreme energies. Some theoretical models suggest that additional dimensions could be folded into our universe at scales too small to detect directly. If a particle were to enter one of those tiny spaces, it would vanish from the detectors without explanation. Physicists search the data carefully for those missing traces. A gap in energy readings can point toward entirely new territory. No experiment has ever ripped open space or generated a doorway to another dimension. The collider tests how particles respond under powerful forces, and every result is uploaded to open databases for anyone to examine. CERN shares updates on its website regularly. The next phase of the project, called the High Luminosity LHC, is designed to increase collision frequency by a factor of 10. That will help researchers catch rare events that current detectors might miss. Proposals for an even larger ring collider twice the diameter of the current one are also on the table. Every new project pushes science into territory it has never reached before. But while physicists were reading patterns in particle trails, the internet was drawing a very different picture, a doorway to the unknown. Could the most sophisticated science experiment on Earth have accidentally lit the fuse on a story nobody planned for? The rumor traces back to a single post in which someone claimed to have spotted an unusual light near one of the Large Hadron Collider tunnels. They described a strange flicker of color near an access hatch late at night. That description caught the attention of readers who follow fringe science news. Not long after, a writer for a satirical website turned that post into a headline declaring that CERN had cracked open a gateway to another world. Many readers accepted it as genuine reporting. Within hours, social media accounts were sharing the satirical article as though it were hard evidence of a classified experiment. Video channels hungry for shocking content started posting clips with titles like "CERN Portal Shocks Scientists." They paired stock footage of flashing lights with clips from lab tour videos and dramatic narration. Each upload promised exclusive footage and insider information, but delivered nothing more than the same satirical text, repackaged with flashier visuals. Search engines made things worse. In the early hours, a search for CERN portal pulled up the satirical piece right at the top. Readers unfamiliar with the source assumed they were looking at an official report. Those misleading headlines flooded the news feeds of millions before a single correction appeared. Conspiracy-focused websites piled on with additional layers. One blog connected the portal theory to ancient stories about hidden realms buried beneath Europe. Another suggested the collider was secretly being used for military dimensional experiments. None of these sources produced any real documentation. Not a single engineer or scientist went on record. Their claims leaned entirely on quotes that could not be traced to any verifiable origin. Fact-checking organizations stepped in to investigate. They combed through CERN press releases, technical reports, and public archives. They found nothing. Their findings confirm that CERN publishes every technical note openly, and that no document of any kind referenced a portal or dimensional gateway. Fact-check sites declared the story false and traced it directly back to misread satire. Max Laughlin encountered the headline in a group chat and immediately set out to verify it. He opened CERN's official news section and found a direct statement ruling out any portal experiments. He downloaded the technical FAQ and came across a passage explaining in plain terms why proton collisions cannot tear open space. He even put together written explanations of what the collider actually does before heading to appear on the podcast. On the show, Rogan and Max walked through the rumor step by step. They traced exactly how a casual post in an online forum transformed into a viral international headline. They played back the original post and held it up against the actual text from CERN. Together, they mapped out how a joke became a sensation. But here is the twist. While Max was tearing down internet myths one by one, real physicists were quietly investigating something far stranger. What if the notion of hidden portals was not completely fictional after all? Physicists have been seriously entertaining the idea that space contains more directions than the three we move through every day. In the early 20th century, mathematician Theodore Kaluza proposed a fifth dimension as a way to unify gravity and electromagnetism under a single framework. Then in the 1930s, physicist Oscar Klein suggested that any such additional dimensions might be curled into loops so tiny they would be impossible to detect. Those ideas planted the seeds for modern theories that attempt to bring all forces and particles under one unified picture. In more recent decades, string theory built on those foundations. It describes the most fundamental objects in nature as infinitely small vibrating strings, and the mathematics behind it requires as many as 10 spatial dimensions. The shapes those extra dimensions take, often referred to as Calabi-Yau spaces, directly determine the properties of all particles. If the shapes were different, the entire universe would behave in a completely different way. String theory does, however, predict an enormous number of possible shapes, which makes finding experimental confirmation an extraordinary challenge. To test whether extra dimensions are real, researchers look for deviations in how gravity behaves at very short ranges. At the University of Washington, the EOT WASH group positions two metal plates a fraction of a millimeter apart and measures the gravitational pull between them using precision instruments called torsion balances. Their measurements down to fractions of a millimeter align perfectly with Einstein's predictions, which rules out extra dimensions larger than that scale. The Large Hadron Collider provides another testing ground. When protons collide at extreme energies, any hidden dimensions could leave a trace in the data. Detectors scan every particle that flies out of each collision, and scientists look for missing energy that would suggest particles escaped into unseen dimensions. After billions of collisions, no unexplained gaps have appeared. Those results push the upper limit on dimension sizes below 10 to the negative 19 meters. Observations from space add further restrictions. Cosmic ray collisions in the atmosphere can exceed even the energies reached at CERN. Telescopes and high-altitude balloon experiments monitor those events for evidence of miniature black holes, which certain theories predict would form if extra dimensions exist at accessible scales. None have ever been detected. Measurements of supernova cooling and the cosmic microwave background also provide indirect checks, and both line up with standard physics without any sign of energy leaking elsewhere. Dark matter continues to be one of astronomy's deepest mysteries. It produces gravitational effects but emits no light and barely interacts with ordinary matter. Some theoretical models connect dark matter to extra dimensions as a way of accounting for its strange behavior. Underground laboratories including Xenon 1T and LEX Zeppelin are designed to catch the extremely rare moments when a dark matter particle might collide with an atomic nucleus inside their detectors. So far, they have recorded only background noise. No confirmed dark matter signal has emerged. String theory broadens the picture further by folding all forces into a single framework and treating particles as tiny loops. The extra dimensions it requires make the underlying mathematics work, but the vast number of possible configurations makes matching theory to our specific universe enormously difficult. Gravitational wave observatories like LIGO and Virgo now record ripples in space produced by merging black holes. If extra dimensions were present, they could subtly alter the way those waves travel through space. So far, every signal matches what standard physics predicts. Researchers continue pushing forward with improved techniques and updated experiments every day. But what if the missing piece is not somewhere in our universe at all? What if the silence in our detectors is the sound of something slipping away unnoticed? What if we have been looking in entirely the wrong direction? Max Laughlin opened the conversation by walking through what actually happens when protons collide inside CERN. He explained that those collisions recreate the conditions that existed in the first instance after the universe was born. detectors capture the flood of new particles that pour out from each impact. By analyzing all that debris, scientists put their theories about forces and the fundamental building blocks of everything to a direct test. He then shifted to the concept of parallel worlds. Max explained that in certain physics models, multiple versions of reality exist side by side, each running on slightly different rules. Particles might cross between those versions when energy climbs to extreme levels. He pointed to the Large Hadron Collider as one of the few places on Earth where energy reaches that territory. He noted that if particles were slipping into a parallel version of reality, it would leave a detectable gap in the data. Detectors would show missing energy. He went through the actual findings and said that every missing energy signal observed so far matches theoretical predictions exactly, which places very tight limits on how easily particles could wander elsewhere. He then brought up the famous double-slit experiment. He described how particles fired through two openings produce a wave-like interference pattern on the other side. That pattern changes the moment anyone observes which slit the particle actually passes through. He used this to illustrate how measurement itself plays an active role in determining outcomes at the quantum level. He said the experiment demonstrates that reality at the smallest scale responds to observation, and he acknowledged that physicists are still debating what that actually means for our understanding of the world. He moved on to the idea that every object vibrates at a characteristic frequency. In his words, matter is not truly solid. It is energy in constant motion. Vibration patterns define the properties of particles and the forces between them. When energy levels shift, particles can appear or vanish. He pointed to the discovery of the Higgs boson in 2012 as a landmark example. That particle explained why some particles carry mass while others do not, and the collider confirmed its existence by tracking the characteristic way it breaks down into pairs of photons and other particles. He then turned to dark matter. He told the audience that the invisible substance makes up far more of the universe than all ordinary atoms combined, yet it produces no light and barely interacts with known forces. Underground facilities around the world have been built specifically to catch the moment a dark matter particle might bump into a detector. None have managed to record a clear confirmed event. He explained that collider data could potentially expose dark matter particles if they showed up alongside known ones, but that has not happened either, which narrows down the list of possibilities considerably. Throughout the whole segment, Max connected precise descriptions of experiments to the larger questions those experiments are designed to answer. He kept everything rooted in data and actual results, explaining each step without losing the thread. He walked the audience through the current state of physics, from the particle showers inside giant detectors to delicate measurements taken in rooms buried deep underground. But here is the twist. The more clearly Max laid everything out, the more one thing became impossible to ignore. For everything we have figured out, the most important mysteries have barely been touched. So what exactly are we still missing? Even after generations of experiments and decades of progress, fundamental questions in physics remain without answers. One of the greatest unsolved problems involves dark matter. The gravitational behavior of galaxies and galaxy clusters points clearly to more mass than any visible matter can account for. Researchers are searching for particles that interact only weakly with ordinary matter. Detectors like Xenon 1T in Italy and Alec Zeppelin in the United States are filled with liquid xenon or argon and designed to catch the faint flash of light produced when a dark matter particle strikes an atomic nucleus. To this day, no confirmed dark matter event has been recorded. Every new run eliminates more candidates and sets stricter limits on what dark matter can possibly be. A second deep puzzle involves neutrinos. These particles pass through the entire planet with almost no interaction at all. Experiments like Super Kamiokande in Japan and Ice Cube in Antarctica track neutrinos arriving from space and from nuclear reactors. They discovered that neutrinos change from one type to another as they travel, a process called oscillation. That discovery earned a Nobel Prize in 2015, but the mechanism that gives neutrinos any mass at all is still not understood. Scientists are planning a major new facility called the Deep Underground Neutrino Experiment in the United States. It will send a beam of neutrinos 1,300 kilometers from Fermilab in Illinois all the way to a detector in South Dakota, with the goal of measuring oscillation patterns far more precisely than before. The search for new forces is equally urgent. Gravity is beautifully described at large scales by Einstein's general relativity, but it has never been successfully merged with quantum mechanics. Projects like the proposed gravitational wave cosmic explorer are designed to detect extraordinarily faint ripples in spacetime caused by some of the most violent events in the cosmos. If gravity behaves unexpectedly at very short distances, those instruments might catch the difference. Plans for the next generation of particle colliders are already in motion. The Future Circular Collider proposed for Europe and the Circular Electron-Positron Collider proposed in China would both reach energies far beyond what the current Large Hadron Collider can achieve. A machine at that scale could produce heavier unknown particles, uncover hints of extra dimensions, or recreate post-Big Bang conditions with even greater resolution. Funding negotiations and site decisions are still ongoing, but the ambition behind these proposals reflects where the field is heading. Another mystery that keeps physicists up at night is why the universe contains matter at all. Theories of the Big Bang predict that matter and antimatter should have been produced in perfectly equal amounts. Yet, nearly everything we observe is matter. The theory of charge parity violation offers a partial explanation for the imbalance. Experiments at CERN's LHCb detector and at the Bell experiment in Japan measure tiny differences in the decay patterns of particles and their antimatter counterparts. Early results confirm that small imbalances exist, but they fall far short of explaining the full scale of the asymmetry. Data collection continues. The effort to build a theory of quantum gravity, one that brings general relativity and quantum mechanics into a single coherent framework, remains one of the most ambitious goals in all of science. Approaches like loop quantum gravity and string theory each propose radically different pictures of what space and time actually are at the deepest level. Neither has yet produced predictions sharp enough for current experiments to test. Quantum sensors using ultra-cold atoms and superconducting circuits are being developed to probe gravity at microscopic scales, where quantum effects might finally become detectable. Understanding the Higgs field more deeply is also a top priority. Since the Higgs boson was confirmed in 2012, questions have emerged about whether it is a standalone particle or part of a richer, more complex structure. Precise measurements of how the Higgs behaves could reveal its interactions with particles that have never been seen. Future collider experiments and dedicated Higgs factory projects are being designed to detect even the subtlest departures from what current models predict. Each of these open questions drives a new wave of research. Physicists across the world work together on these experiments, share their data freely, and continuously sharpen their theories as new results come in. The road ahead is long, but every unresolved question points toward discoveries that are still waiting to be found.